Greetings and welcome to part 2 of the tone stack video series. In part 1 we talked about the different types of tone control, the active and passive. We talked about the locations within the amp circuit and the results, the good and bad of placing them in different locations. And finally we discussed some general rules regarding capacitors and how they're affected by the frequency of the signals that try to pass through them. And we ended up creating a high-pass filter and a low-pass filter with a frequency output graph for each and a cutoff line right vertically here that told the point at which 100% of the frequencies would pass through and show the attenuation of the frequencies that were either lower than the cutoff in a high-pass filter or higher than the cutoff in a low-pass filter. Now, that's all fine and dandy, but wouldn't it be nice to be able to move the cutoff point? You could completely change the nature of your high-pass filter, which is your treble control, or your low-pass filter, which is your bass control. If you could move these cutoff points either left or right, you could alter the effect that the tone control has on the sound of the signal coming through the amplifier. So let's talk about what determines the location or the frequency of the cutoff point and what can we do to move it left and move it right. And we will see that this formula here determines the location of the cutoff point. Now I know some of you are gouging your eyes out at the sight of some scary formula like this. But look, just sit back, okay, take a Valium, relax, and let me try to explain to you how this works, and I guarantee you at the end it will all make sense. Okay, the location of the frequency cutoff, left or right, is determined by this formula, 1 over 2 pi times the resistance that you use in the filter and the capacitance that you use in the filter. Remember, each of the filters, high and low pass, used one resistor and one capacitor. Now they were put in opposite configurations for each filter, but this is how they were built. So let's look at a sample here. Now this is a low pass filter because, as you can see, the high frequency has a route to ground. We'll say that this low pass filter has a 5K resistor here. That's 5,000 ohms. And a 0.05 microfarad capacitor to ground. Okay, using our formula, we want the resistance in ohms, which is going to be 5,000 ohms, and we want the capacitance in farads. Now this is a little tricky. So here where I have 0.05 microfarads, to convert microfarads to farads, you add 6 zeros. So here I have 1 0 between the decimal point and the number. I'm going to add 6 more, and I'm now going to have 7 zeros between the decimal and the 5. If it were in nanofarads, I would add 9 zeros, picofarads, 12 zeros. Okay, I know your blood pressure's up now. Just relax, it's going to get a lot simpler. Let's put the numbers into the formula. 1 over 2 times pi, which is 3.14, times 5,000 ohms, times 0.7 zeros and a 5 for the capacitor, which is in farads. I left the F off here. Not good for a math teacher. And that's going to equal 1 over 0.00157, which is 637 cycles per second. So the frequency and output graph of this low-pass filter would be that the cutoff point is right here at 637 cycles per second. Everything below that is passed at 100%. Everything above it is attenuated, and the higher you get above it, the less the capacitor is going to let through. Now that we've suffered through that math, I'm going to really excite you here when I tell you none of that really matters. Okay, so if you didn't follow it, it doesn't make any difference. Here's what you have to take away from the formula. And that is, since the resistance and the capacitance are in the denominator, it means that the frequency cutoff is inversely proportional. Okay, a scary term. What that means is, as these numbers go up, this number goes down. As these numbers go down, this number goes up. So if you want to move the frequency cutoff to the right, which is up, which is higher frequency, then lower the resistance or lower the capacitance in your filter. You want to have your low-pass filter not go as high as 637 cycles per second before it starts attenuating. Well, if we want the cutoff to go down, we will increase either the resistor to say 6,000 or 7,000 ohms, or we'll increase the capacitor to 0.07 or maybe 0.1 microfarads. By increasing these values, either one or both, you will move the cutoff point to the left, and your low-pass filter will be more selective. It will only allow, your bass control will only allow the lower frequencies to pass and not so much mid-range. By the same token, if we want to open up our bass control and let more frequencies through, a little more mid-range through, we want to move the 637 higher, then we will lower these values. We'll go down to 4K, or we'll go down to 0.005 microfarads. So by lowering the capacitance, or lowering the resistance, or both, we'll increase the cutoff value and move the frequency cutoff to the right. This is what you need to know right here. The math explains why it happens, but this is really what is happening and how you can modify your own tone controls by following these two rules. Okay, after that math nightmare, let's go see what Rusty's up to. As Rusty fans all know, he is a dedicated photographer. And today I'm going to prove just how dedicated he is. On the left we have a fabulous digital camera. On the right, an old dried out wretched bone. Let's bring him out and see which he picks, and you know darn well it's going to be the camera. Ready? Here he is. Rusty, the camera is right over there. Look at that camera. Do you want the camera? You don't want the bone or the camera. Rusty, there's the camera right over there. I know you prefer the camera, don't you? Well, okay, on to step 2 of this test. Now, test number 2. Fabulous camera, indicative of photography career, or old wretched blue broken fly swatter. Here he is. Rusty, the camera's right over there. Don't you prefer the camera? Well, so much for these tests. Okay, enough play. Let's get back to work. Before our break, we learned how to calculate the cutoff frequency and how to move it left and right. We found that if we wanted to move the cutoff frequency to the left, we would increase the resistor or capacitor or both in our filter. And this works for high pass as well as low pass. If we want to move the cutoff point to the right, we will reduce the value of the resistor and or the capacitor. Now let's move on to a direct comparison between two of our favorite brands of amplifier. Okay, here's a direct comparison between a Fender tone stack and the Marshall tone stack. Now I know there's some variations from amp to amp, but this is really what you need to see to understand why they are so different. Also, let me add that I grew up in an area where Fender amps predominated, so that's really my specialty. I know there are people that absolutely worship Marshall amps, and I know that the tone is very different, the output characteristics, so let's see why. First off, I think you'll be surprised to see how similar they are. The overall architecture of the two tone stacks is virtually identical. The differences lie in the values that Fender chose in these key locations and the ones that Marshall chose. Let's also look at the different components within the tone stack. Look here, we have our input coming in, And everything I say about the Fender is going to be true about the Marshall, so you can kind of apply it over here. Otherwise, if I repeat myself, it'll get boring and make the video 9 hours long and cut down on your pole dancer viewing. So let's come in here. Now, this is the high pass filter. This is the treble control. And the values that Fender chose, remember it's capacitor, then resistor. Fender chose 250 picofarads for the capacitor, 250K for the resistor, and Marshall chose 470 picofarads, which is about double for the capacitor, and about 220K for the resistor. So the resistance is about the same, but the capacitance is twice as high in the Marshall tone stack. What did we just learn about this? As the capacitance goes up, what happens to the cutoff point of the high-pass filter? Hopefully you said the frequency cutoff will move down to the left, because this capacitance is about double this. Higher capacitance, lower frequency cutoff. Now let's look at the low-pass filter. In the Fender, and remember low-pass filters have resistor first, then capacitor, chose 100K resistance, 0.1 microfarad capacitor, and then this would be your bass control here, the volume control for the bass, if you will. Okay, but look at what Marshall has done. They've gone way down in resistance, and they've gone way down in capacitance. What does that tell us? When the values go down, what happens to the frequency cutoff of the Marshall tone stack? It's going to be way to the right, much higher than in the Fender tone stack. So the Marshall is going to allow a lot more low and mid-range frequencies through than the Fender. And finally, just to keep it simple, let's look at the mid-range. Look, if your high frequency takes this route, your low frequency takes this route, what do you think's left? The mid-range? In other words, the frequencies that were more or less attenuated here and more or less attenuated here are finally going to have their day in the sun and come down here and find a capacitor and a resistor that suits them and allows them to be expressed in the output signal that is allowed to pass through the tone stack. Let's look at the values. 0.047 microfarad for the Fender, 10K for the resistor. Okay, this is actually similar to a high-pass filter, but the capacitance is chosen to favor mid-range. Okay, let's look over here. It's half the capacitance, but 2.5 times more resistance. So in this case, it's sort of a draw, actually, on the mid-range of these two. In this case, the capacitors then would favor a lower mid-range for the Marshall, and the resistors would tend to favor a higher mid-range for the Fender. And I'm going to say that's sort of a wash. Now, let's look at the total resistance to ground in both tone stacks, because this can give us an idea of what the gain of the amp is going to be. Fender puts 250K, 250K, and 10K between the input and the output. Now granted, as you adjust the tone controls, that will change. And all three tone controls, it must be said, on passive tone stacks tend to interact a lot. When you turn the bass control, you're really affecting the treble and mid-range. Now on active controls, that's not the case. They are separate. You control the treble independently of the bass. But in the Fender type of passive tone stack and the Marshall passive, they're totally interactive. So there are no absolutes. Like I said, when you adjust the treble, you're also affecting the mid-range, because there's this overall stack here of resistance to ground. Now the Fender has, what, 510K to ground. Look over here at the Marshall. 220, 1,025K. Okay, that's going to be what? 1,245K, which is considerably higher over double what the Fender tone stack has to ground. What that tells us is the more resistance you have to ground, the more gain you're going to get out of the amp. So with our Marshall, we're going to get different tone characteristics based on the fact they chose different values for their high pass and low pass filter, and we're also going to get more gain than we do out of the Fender amp. Okay, let's summarize the respective differences between the Fender and Marshall tone stacks based on the component values. We said that as far as the high pass filter goes, Fender's frequency cutoff would be moved to the right compared to Marshall's, which would be further to the left. Low pass filter, just the opposite. Fender's frequency cutoff moved to the left, Marshall's at higher frequency to the right. Mid-range I thought might be a draw, but the Marshall's mid-range capacitor is about half that of the Fender, so let's just make a guess that the mid-range will be very close as far as the cutoff points, and that the Marshall might be just slightly to the right compared to the Fender. And then finally, gain. And the Marshall is going to have it all over the Fender amp. Okay, the Marshall, because of its very high impedance to ground compared to the Fender, is going to have a lot more gain. Now I'm going to introduce you to a just absolutely miraculous program that you can download for free on the internet, and I'm also going to include a link in the description of the video to help you find this download site and download the Duncan Amp Tools Tone Stack Calculator. In a few seconds I'll demonstrate the program and how to use it, but here I'll just give you a little preview. It's going to show you the Fender tone stack and allow you to go in and double click on any of the components within it and change them. Say you want to change that to a 0.2 microfarad capacitor, click on it, put in the 0.2 value, and then it will show you the spectrum, the different spectrum that you get based on that change. It saves you hours and hours of trial and error of, with a circuit and plugging in different components, and this can show you exactly the type of tone that you're looking for and the modifications you need to achieve it. So without further ado, let's take a look at the Duncan Amp Tools Tone Stack Calculator and see the audio spectrum of the Fender, the Marshall, and we'll throw in a Vox and also a James type of tone stack. Now the James is a passive type of Baxandall tone stack. Everybody's heard of Baxandall. It's primarily used for hi-fis and stereos, and we'll see why in just a minute. Okay, here we are looking at the tone stack calculator, and here is the Fender tone stack that we've been looking at through both parts of this video. And over here is the audio spectrum that would result from putting a 0 to 20,000 cycle per second tone into this tone stack with all of the controls set at 5, which is mid-range. Now, a bunch of you are wondering, why does this spectrum have this monstrous dip right in the middle? There must be something wrong here. Most of us have come to expect the output from tone controls to be flat, but it isn't in most guitar amplifiers, and the reason is that it is scooped in the mid-range to compensate for the fact that most guitar pickups put out a very mid-range intensive signal. In other words, the guitar pickup, be it humbucker or single coil, is not real good at portraying bass or treble frequencies, but it's dynamite in the mid-range. So if you flip this over so that it more or less turn it upside down, where the peak was up here in the mid-range, you would see then what the output looks like from a guitar pickup. When you put the two together, this compensates. If you had a flat output from the amplifier tone stack, you would have a tremendously mid-range tone coming out of the amp that might not be pleasant at all. But this compensates for the high mid-range of the pickup, and you end up with a much flatter output from the amplifier due to the peculiar spectrum of the pickups and the compensating spectrum of the amp. I hope that made sense. Now that we're getting over our shock of seeing the Fender spectrum, let's come up here. We're going to take a snapshot of it, and let's look at the Marshall and see if our predictions are true. Okay, now some of you I know are probably reaching for your blood pressure medication, because as you can see, there is a tremendous difference between the two spectra. First of all, we predicted that the Marshall would have much higher gain, and as you can see, this is like loudness, okay, going up the y-axis here, and the gain is much higher for a Marshall amp. Put the same signal into both, and you're going to get a lot louder sound out of the Marshall than you do out of the Fender. Next, let's look at the spectrum here and see if our predictions were correct, and in so doing gain some sort of comfort or experience with analyzing the cutoff frequencies in the spectra. Okay, first let's look at the high pass filter. Over here, where the frequency cutoff will be is where the graph starts to get flat. In other words, the frequencies are starting to be passed at 100%, and it looks to me like that's right about here on the Marshall, and on the Fender it is indeed shifted to the right and would be right over here. So there is a big shift to the right as predicted on the Fender spectrum. Next, we said the Fender on the low pass filter was shifted way to the left. Where would you say? Was that about the high frequency cutoff for the Fender? And look up here where the Marshall is, way over here. You see where it starts to get flat and then it's starting to attenuate. So that would be the frequency cutoff for the Marshall, and the Fender is way to the left, exactly as predicted. The mid-range point we said would be pretty close, and it really is. The mid-range is going to be the trough here, and looking here on the Marshall, we said it's either going to be pretty even or maybe a little to the right of the Fender, so I'm going to say that's the mid-range frequency cutoff right there, and slightly to the left, as predicted, would be the Fender mid-range cutoff. So it would appear that the spectrum, the shape of them and the way they compare would be exactly what was predicted by looking at the respective component values between the Marshall and the Fender, and also that the gain of the Marshall is much higher because its impedance to ground is much higher. Less of the signal leaks to ground in the Marshall amp than it does in the Fender amp. Next, let's take a look at a Vox Spectrum. Now I want you, those of you who have more experience with Vox amps than Marshall amps than I do, like I said, I tend to have worked mostly on Fender amps. Where do you think it's going to be? Is the Vox going to look more like a Marshall or more like a Fender? Okay, let's take a snapshot of the Marshall so it stays, and here comes the Vox Spectrum. And look at that. It is essentially a Fender Spectrum with all of the cutoffs shifted slightly to the right. But the gain is fairly close, and the frequency cutoffs are fairly close. Okay, so those of you who have a Vox amp, what you're getting here is really this very similar audio spectrum to a Fender, except with the frequency cutoff shifted a little to the right. Let's take a snapshot of that, and then let's look at the James or Baxandall type of output spectrum. And look at this. Now, as I told you, it's nearly flat. It will not compensate for that big mid-range peak that you get from the pickups of a guitar. So if you use a James or Baxandall type of tone stack, you're liable to end up with a very, very mid-range intensive tone from your amp. If that's what you like, maybe the James and Baxandall tone stack's the way to go. I think, though, for most of us that grew up accustomed to this scooping in the amplifier to compensate for the pickup mid-range intensity, the sound from the Marshall, Vox, and Fender will be more what we're accustomed to hearing. Now, using the mathematical relationship between capacitance, resistors, and the position of the high frequency and low frequency cutoff, let's turn the Marshall spectrum into a Fender spectrum. It's going to be higher gain. It's going to be a loud Fender spectrum. But let's see if we can do it. Let's modify a few of the components over here. I'm going to show you how easy it is to do this, and we'll turn the Marshall amp into what sounds exactly like a Fender amp. Step one, let's look over here at the low end. There is a big difference in response between the Fender and the Marshall. And I think it's because of this capacitor right here. So I'm going to double click on that 22 nanofarad capacitor, and I'm going to change it. I'm going to make it 10 times higher just to see what happens. I'm going to put in 200 nanofarads and say OK. And look, now it is louder because it's higher, but it follows the same curvature in bass response. It's very close. High-end response is very close. But we have a little problem here in the mid-range. So now let's look down here at the mid-range capacitor. And what is it? 22 nanofarads. Well, let's see. Let's go to 50. We'll double it because we really are not that far off. And let's say, okay. All right. What we did then, because we went up in capacitance, we brought the trough, or the what amounts to the frequency cutoff, down. Went up in capacitance, down in frequency trough. So look, they do coincide here, but it's not quite as sharp. So what I'm going to do is come over here and change the potentiometer for my mid-range on the Marshall amp. And instead of 25K, I'm going to go down to 10K and say, okay, let's see what happens. Boom. Now, if you look at these, I think you'll see that they're almost exactly parallel. That means that the audio spectrum here from the Marshall amp would be virtually indistinguishable from a Fender amp. It would be louder. You'd have to turn the volume down a little bit to equal a Fender. But because of these changes, 1, 2, 3 component changes, I have turned a Marshall amp into what sounds like a Fender amp. Well, that about does it for this two-part video series about tone stacks. I know a bunch of you will be hurrying over to the Duncan's Amp Tool site to download your tone stack calculator. Those of you who like to modify amplifiers and fine-tune them will find this to be a wonderful tool to help you. It speeds your progress because you don't have to do a lot of trial and error. You can go in here and make the component changes and then see exactly what the spectrum is going to be like. On that happy note, Rusty and I are going to bid you a fond farewell. We really appreciate your loyalty and interest, the time you spend watching our videos, the comments that you make and suggestions, and we just want to wish you all the best. Okay, thanks for watching, and we'll see you again soon. Bye for now.